Okay. Um, wow. 2 weeks from today, you'll be taking your last test, your test number 3, your final exam, whatever you want to call it, all meaning the same thing. Next week, we will be looking at graphs. And today, we're going to look at 3 things. First thing is, and like I said, if you watch the videos, a 2, 3, 4 tree. The second thing is a red-black tree. And we're going to see how that guy is related to this one specifically. And then we're going to take a look at something pretty quickly called a B tree. And the reason we can do it quickly is because it sort of comes out of here. This is just a specific B tree. When you watch the video, you know there's all different types of B tree. But we're going to start with what's specified as a 2, 3, 4 tree. Now, yeah, we've been doing binary trees. A node, a node, a node, a node, a left and a right, a 0 and a 1. You only have 2 choices. We would store one thing up here, the number 6. And from watching the videos, you should understand that I didn't get very far. The 2, 3, 4 tree is going to actually have a node, and how many possible values can be stored in that node? No? Nobody? That's telling 3 values. A 1, a 6, and an 8. This is a 2, 3, 4 tree. It has, instead of 2 parent-child relationships, this parent can go down to 4 different children. This parent has 3 values. So you start to see the 3 and the 4. Not sure where the 2 comes from, but this is going to be a 2, 3, 4 tree. It is no longer a binary search tree. It is just a search tree. Inside a node, I can store up to 3 values. So my question then is, this is 3 values. If I used a tree of height 2, how many values could I store?
It's 7.
Well, I could store 3 more in this node, 3 more in this node, 3 more in this node, and 3 more in that node.
So 15.
15, yeah, 15. And oh boy, if I kept going, with this guy, I could do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There's another 12, 12, 12, and 12. That's another 48, which would give me how many? I could store in a height of 3.
Is it 66?
63. And I wonder what the next number would be. Well, in pre-calc, you learned a whole bunch of sequences and series, etc., etc. What would this next number be? Do you see a pattern? Well, this is almost 4. And the reason I say that is this is almost 16. And this is almost 64.
Is the next number 255?
Yes, sir. This is 4 to the 0 minus, well, this is 4 to the first minus 1. This is 4 to the second minus 1. 4 to the third minus 1. 4 to the fourth minus 1. So when you were doing this back in pre-calc and your mind was really focusing on how to do these, yeah, you were hitting these like crazy. And the next number would be 255 total values that I should be able to find quickly by searching. Is it in here? No. Is it down one? Oh, it's down this path because it's between 1 and 6. Ta 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 ta. Okay. And of course, you see where the 4 comes, it's one more than that. Maybe that's a pattern. So if I gave you some information about the 2, 3, 4 tree, you're like, yes, I watched a video. I could do this quickly. 2, 3, 4 tree is another abstract data type we continued to learn throughout this semester, where we would have to figure out how to construct it, find out if it's empty. You know, it's empty if this first node is empty. How to search through. Is it in here? No. Is it down which pointer to the next node? Yeah, I have 3 values, 4 pointers coming out of here. So when I did my struct, I'd have all that going. How would I insert a value? How do I delete a value? Well, that's a lot. And, you know, our semester is winding down and we're starting to hit concepts instead of detail because the concepts are harder, which means lots of detail would take a long time. So if I said, okay, let's build this, first number 53, it's going to go in and it's going to be stored there. Second number 27. Ooh, hey now, 27's good, except it's going to come in here and it's going to bump the 57 over. 75. Yep, there's room. It's going to sit right there. Right there. So I have 3 numbers. I could quickly search and find to see if those 3 numbers are in. Continuing on. I now want to add 25. Uh-oh, there's no room, so this guy splits. 25 and 27 are going to come down into a new node. Let's make this look pretty. 25, 27, and something. So the 25, when I tried to put it in, came on this side. It made this side overweight. So I split it. 27 goes down with the 25. The 53 moves over and the 75 goes down. Okay. Again, what did I just have? I had 27, 53, and 75. My next number was 25, which made that side too big. So I split it. 25 and 27 went down to the left. 53 moved to the right. 75 went over. So there's lots going on when I insert. If it's already full, I break it and send it down, etc., etc. Next number is 70. I come here. It's greater than 53, so it's going to go down this path. It's going to move the 75 over and give me a 70. Why do you get pencil out? Well, I think you know why I got pencil out. Okay, so far so good. 41 is less than 53. Oh, nice. It's going to go right in there and store safely. Next number, 38. 38 is less than. It's going to come in. It's going to go wobble, wobble, wobble. It's going to sit on that side. And now I do a split. But this time when I split, I'm going to send 27 up because there's room. I don't need to start a whole nother layer yet. So after that initial one and going down, now I'm going to see if I can split and go up. And I can. So up top goes the 27. The 53 gets moved over. To the left of 27 is going to be Mr. 25. Coming out of here is going to be the 38 and the 41. And yeah, I just have empty stuff hanging out over here. This going to be good for searching? Yeah. Yep. Once all the code is written to get all this set up, it's going to go for quicker searching. All right, so I just put in 38. Caused chaos. It sent one up. If I send one up now and this gets full, then I got to do a split again. After that initial filling, I'm going to send it up. 38. Fit in there pretty nice. 16. It's less than, oh, so this 25 has to move over and the 16 is going to go in the beginning. Somebody's not using pencil. I don't know why. 59. Let's see. It's greater than, well, it's going to slide right in there. 36 is going to go here. 36, 38, 41. Again, I don't know why I wasn't doing that in pencil. 73. Gonna write out there on the end. 65 is greater than. It's going to come in here and it's actually going to bump this 73 over. Uh-oh. 60 is going to come in here and it's going to weigh down this left side. So we're going to split. We're going to send 65 up. So now I'm going to have 27, 53, 65. Well, if I have to send something else up again, it's all kind of craziness going on. To the left of the 27 is the 16 and the 25. There it goes again. Coming down here, I have 36, 38, 41. Between 53 and 65 is going to be this 59 and 60. Now out here is going to go my 73. Next number, 60, is going to go there. I got 60. The next number is 46. It's going to go in here. Oh boy. 46 is going to go in there. That says, ooh, split and send one up. But when I send one up, what's going to happen? Another split. Another split. Okay. Pausing the video. I want you to take a couple of seconds. Where in the heck's pause? There it is. Take a couple of seconds and draw out and see what it looks like. Awesome. Thank you. So when I put 46 on this side, made it heavy, I sent the 38 up. So now the 27 and the 38 are buddies. So they're going to be to the left of the 53. 70 is going to be to the right of the 53. 16 and 25, still less than 27. The 36 that broke away is going to be between the 27 and 38. and the 41 and 46 are going to be to the right of the 38. Over here's the 70, still the same. To the left of 70, Wonka, 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 and to the right of 70, Willy, Willy Wonka. You got it, or you want to try one on your own? Can we try one on our own? Okay. Do, 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 do. Breakout rooms, do, do. Now I'm pausing again. Resume recording. There we go. Here's what I got. 70. 17 and 70. 5, 17 and 70. I added the 23 and it split. That's that initial almost one-time deal where we're filling in the top. Now we're going to start to fill down. Okay. I have 31, 11, and then I got to the 48. I got to the 48 and boom, 31 had to go up, 23 to the left, 48 and 70 to the right. I apologize for my sloppiness. 21 went in, pretty nice. 19 went in, fairly nice. 3 went in nice. 6 is not so nice. So this is my first one where I'm going to split and the 5 goes up. 5, 17, 31. To the left was the 3. To the right was the 6 and 11. Over here, I had the 6 and 11. Whoop, to the right. To the left, 19, 21, 23, 48, 70. Okay, the next number I added was, I did the 19, the 3, the 6 caused havoc, 68. The 68 is going to come over here. I add 75. So I added 68, nice. 75 causes havoc. 68 goes up. That causes havoc. So now I had the 17, 5 to the left, 31 and 68 to the right. To the left of 5, I still had 3. To the right of the 5, I had the 6 and 11. To the left of the 31, I had the 19, 21, and 28. 31 and 68 between them was this 48. To the right of them was the 70 and the 75. So if you didn't get to finish, screenshot it, take a picture, come back and watch the video later. But 2, 3, 4 trees. Good. Moving along, the next thing, number 2, red black trees. Okay, so there I have a 2, 3, 4 tree sitting there, and we know it's not a binary search tree. But what if I said, I love the concept, but can I change this into a binary tree? And the answer is yes. And if you take a look at some of the rules to turn this red black, or excuse me, so we're going to turn a 2, 3, 4 into red black. And that red black is going to be binary. Okay. Siblings. Oh, my pointers. My pointers are now going to be either red pointer or black pointer. So now I'm going to have to add more to this struct. Not only am I going to have a spot for 3 values kind of deal, I got more and more and more going on here. A parent, 2 siblings are going to be connected by a red pointer. We'll talk about the struct a little bit later. A parent to a child is going to be connected by a black. So if I get ready and start, and I say, okay, I have these 2 numbers, 21 and 34. Pick a number. Which one do you want to start with? Pick one.
21. 21.
21. So here's going to be 21. And I know in my world, 34 is to the right of it. And we just said siblings have to be connected with red. Siblings are connected with red. Okay, so 21 has children, 18, 19, and 20. Well, the middle one is 19. To the left of 19 is 18. To the right of that is 20. And our rules said siblings have to be connected by red, and parent to child is connected by black. Uh, 34 has two numbers coming down. First one is 37. It's excuse me, we got to take care of this guy first. The 25. 25 is greater than 21. It's less than 34. So the 25 is going to go there, and it's going to be connected as a child. Here's a child. That was that left one. Here's a child. And actually, we're going to have another one coming over here. Pick a number, 37 or 40.
37.
37, which is fine. And it has a sibling, which is greater. And we're going to connect that by red. So a 2, 3, 4 search tree can be represented as a binary search tree. Don't ask me when we would use this. This maybe I could see. This, boy, some other rules that come along with this. Every path has the same number of blacks. Well, there's a black down to the 18, down to the 20 is a black, and one black. If I had another level, all of my paths would have two blacks. Okay? You will never see two consecutive reds. Why? Because the middle one will be here and the siblings will be to the left and to the right. Okay, that is a red-black tree. Well, that was kind of brief. Let's see what we got here. Let's build one. Let's build one. Not yet. Let's do another one. Let's do another one. Yeah, you got a little sloppy there, Hoss. I know. How about on your own without going into groups? See if you can come up with it. And you may have to use R's and B's. I knew to plan ahead. I got more colors than you. Yep, as you can see, 41 is a sibling with 46. So it would go to the left and it would be red. And again, two blacks, two blacks, two blacks, two blacks, two blacks. Exact path has the same number of black links. No two or more consecutive red. They were our only two rules. All right, well, that doesn't make sense to do this when I already have this done. So let's see if we can do one on our own. And I just can't find my paper. Let's get another piece of paper. Okay, some numbers. 53, 27, 75, 25, 70, 41, 38, 16, and 59. 2, 3, 4 tree. Sha boom, there is 53. That's nice and quick and done. And red black tree, you know, this would be 53. Next number is 27. So I'm going to add 27 to the left. 27 is less than, and that would be a right, or excuse me, a red. Next number is 75. This would be greater than, so it's 75, and that would be a red. Okay, so far not too bad. Again, do the examples, do the examples, do the next number is 25, and it's going to weigh this down. So I know this guy turns into a 53, 25, 27, and a 75. Let's see, I just added, I did 53, 27, 7, 25. When I come in here, I'm now going and saying, oh, 25 is going to sit here. Okay. And what happens? Well, let's see. Because this got split up, my red and blacks are going to have to change. 25 and 27 becomes a red. Because of the split, this guy now became black, and this guy became black. So when I get two consecutive reds when I'm building, I need to make some kind of changes. All right, the next number is 70. And let's see, I have 53, I have 25, 27, 70, and 75. So I added 70, which is greater than 50. 70 is going to go there, and it became a sibling. Oh, okay. I'm starting to figure some of this out. I didn't have splits, so I didn't have to change reds and blacks. I threw the 70 on, and it's still okay. Throw the 41 on. That's going to go less than. That's a sibling. So when I add it, it goes to there, it goes to there. It's to the right of 27, and it gets added as a sibling. And I don't have any of that like percolate up or percolate down kind of stuff happening. The 41 was a happy number. And now we're going to add 38 and go, oh boy, that's going to make some changes. So the first thing is, I'm going to do it this way. I have 27 goes up and joins 53. I have 25 to the left. The middle is going to be 38 and 41. And to the right would be 70 and 75. Okay, so let's see. I had all of this. I had 53 was the big boss, 27, 25, 41, 75, and 70. That was a black, that was a black. These guys were reds. And I just added 38. 38 is less than, is greater than, is less than. And when I add 38, do you notice it becomes a sibling because I added it? Oh, nice. But now stuff has to change because I have two reds in a row. Well, if these two are siblings, this can no longer be a red. So this had to become a black. This guy, because he became black, had to become a red. Scribble that out. 25 also had to become a black. Everything over here was still good. So once something happens, I need to go back through and be changing reds and blacks. Okay. Just keep going. That was 38. The next number is 16. In this 2, 3, 4 world, it would look like that. In this world, it's less than, less than, less than. It would go there. And I don't have two reds in a row, so it's okay. Now, to do all those operations when we're inserting, this becomes a red and it was a red before, then all kind of stuff has to happen. It all's happening because of that split. So you need to know how to do the 2, 3, 4s before you can do the red blacks because they do parallel. Yeah. Questions? Questions? Okay. The last thing, B trees. B trees are like 2, 3, 4 trees. Here is the 2, 3, 4 tree. And we already discussed if M is 4, it can hold 3 values. Okay, it can hold 3 values. And we got that 4 to the first power minus 1, 4 to the second. We talked about that a little while ago. Back in the world of our binary trees, we had the same kind of thing going on, right? I can hold 1, 3, 7, 1, 3, and 7, and 15, and on and on. So depending on what the height is, and there's always that argument, is the height 0, 1, 2, and 3, or the height 1, 2, 3, and 4? To me, the height is 1, 2, and 3. We don't start with 0. The book, when it talks about it in this table, actually uses 1, 2, and 3. What about 10 values? Well, my first row could hold 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, second row could hold 99, 999. Yeah, but there'd be a lot of switching up. But these are called B trees. B trees. Has M minus 1 pieces of data. When the B was 4, it held 3 pieces of data, and it has 4 pointers. And if I went with 100, we could store a lot fast and not have to search long, but boy, there'd be a lot of pointers. And imagine creating a struct when M is 10, having 9 data spots with 10 pointers shooting out. Okay. Questions? I didn't rush, but I wanted to get to it because I know I had one leaving and then another one leaving and so on and so on. But questions on 2, 3, 4 trees, red, black trees, or this generic 2, 3, 4, which is, any of it, any value I want to pick for M. No?